We're going to prove the sine rule. Most of you are familiar with what it is, and you're going to see it soon enough. It involves two cases. In the first case, triangle ABC is acute. That simply means all angles of triangle ABC is less than 90 degrees. So right over here, I have a picture of triangle ABC. I dropped a perpendicular from point C to side AB. Okay. Excuse me. So what I'm going to do is I'm going to consider the right triangle BDC, and I'm going to write the following based on the very definition of sine of an angle. So sine beta is CD or DC by BC. And that implies if I multiply both sides by BC, I get the following. DC is equal to BC times sine beta. Now, I'm going to put it here. I am going to do the same thing with triangle ADC. And using the very definition of sine alpha, which is really angle CAD, I can say the following. Sine alpha is equal to opposite by hypotenuse. And that allows me to draw the following conclusion. DC is equal to AC times sine alpha. Now, look what just happened. We expressed DC in two forms. And that's good news for us because let me do it nicely so that we understand what's going on. DC is equal to BC times sine alpha, and DC is also equal to AC times sine alpha. Now what can we do? We can combine them and see what we can do. From this, we can draw the following conclusion. DC, since DC is equal to itself, I can say this. Okay, this is very important here. Okay, now I'm almost done. I'm going to do one thing. I'm going to erase these things. I don't need them anymore. I need the room. So what do I do here? I divide both sides of this equation by sine alpha and sine beta. How do I do that? Well, let's do it right here. I'm assuming neither one is 0. And I'm going to do it here too. So this is much better. And now I can do some cancellations. I can cancel this and this, and I can cancel this and this. Now, remember, instead of BC, I can write small a. Instead of AC, I can write small b. Instead of BC, I'm going to write small a. Instead of AC, I'm going to write small b. And I did some cancellations, as you can see. AC is, once again, small b, and we have our traditional looking sine rule or sine formula. We just did it for acute triangles. We are now in the next video, or in the next part, we're going to prove it for obtuse triangles, which is a little extra work, but nothing beyond us. And by the way, you can do the same thing with the other pair, small c, and you can call it sine gamma, the angle C. Same way it can be done. So this is part 2 of our proof. In this case, we're going to call it case 2. In this case, the triangle ABC is obtuse. What's an obtuse triangle? In an obtuse triangle, there is exactly one angle that's larger than 108, that's larger than 90 degrees. So in our example, angle ABC, which I've labeled as beta, is larger than 90 degrees. In this case, we drop a perpendicular from point C to AB extended. We call this perpendicular line AC, or you can call it line segment. I guess that's a bit more accurate. Now, what I'm going to do here is I'm going to do something very similar to what I have done. I will express CE in terms of alpha and beta. I have to do a little extra work. Okay, so let's get to it. I am going to write, considering triangle or right triangle CEA, okay, I can say the following. I'm looking on right triangle CEA, and I can say sine alpha is equal to opposite CE divided by AC. Okay, now AC is really small b. Okay, if I multiply both sides by AC, I get the following. I get the following. Fine, let's save it here. Now I'm going to look at triangle BCE, right triangle BCE, and the right angle is at BEC. BEC is the right angle. And I can use that right triangle. If you really want to be particular, this is the triangle I'm working on, okay? I don't like my pen mark, so I'm going to erase it. You know which one I'm talking about. So I am going to use that right triangle to write, and I have to be careful. I cannot use sine beta, but I have to use sine. By the way, alpha and beta are in degree. Should have mentioned it, but now I'm mentioning it. It really doesn't matter, but I'm going to assume it's in degree because I'm using 180. They can be in radian. The formula is still true. Now let's explain this. This angle is beta. this has to be 180 minus beta. Since I'm talking about triangle BEC, I better use the correct angle. I can't use beta. Now, this angle is equal to, this angle is equal to sine of 180 minus beta is equal to opposite divided by hypotenuse, which is BC. Now, a little extra work here. Now, if you remember the properties of the unit circle and all the things we have done, you do know sine is the y coordinate. And if you visualize the unit circle, you're going to see sine 180 minus beta is same as sine beta. Okay, that's one way to do it. Another way to do it, if you do the difference formula for sine and expand it and evaluate cosine 180, which is -1, and sine 180, which is 0, you're going to get the same thing. Let's do it. Might as well do it. So I'm going to do it the old-fashioned way on the side. Let me go to another slide and do it. I'll save it here, okay? So I'm going to show you this, and it's fun. Sine 180 degree minus beta, which is in degree, understood, is equal to, remember, sine 180 degree cosine beta minus cosine 180 degree sine beta. Now, sine 180, sine is the y coordinate, blah, blah, blah. That's 0. So I'm going to replace this with 0. All right, cosine 180 is -1, interestingly enough. Okay, so I'm going to replace this with -1. Hopefully you're with me so far. Okay, so this one can be erased completely. 0 times another number is 0. And that -1 and negative, they kind of cancel, and this is what you're left with. By the way, I should have deleted this, made a little error here. Let's go back and fix it. Errors seem unavoidable. Or they like me very much. Okay, so here we go. So -1 times negative, they cancel right here. Sine 180 minus beta is equal to sine beta. So that was a little bit of a detour. Let's get back to our main problem right here. Now, I'm going to take this and I'm going to replace this with beta. Now I'm in good shape. I'm going to multiply both sides by BC and I'll see what I can get. Multiplying both sides by BC allows me to write this. Now, the good news is I've just expressed CE in terms of 2 different expressions. Right here and right here. I don't care about the rest. Let me get rid of the other things, okay? I'm going to get rid of this, and this. Now, I have 2 ways of expressing CE. Therefore, I can draw the following conclusion. Okay, and let's go ahead, replace BC with, replace BC with small a. Might as well do it now. BC is small a because it's facing angle capital A, and AC is small b, it's facing angle capital B or beta. Okay, now as before, I'm going to divide both sides by, now let me get, if you don't mind, I'll get rid of this. And let's fix it. It's obtuse, no obtuse B. Okay, now this is where we are. I'm going to divide both sides of this equation by sine alpha times sine beta. And hopefully I'll be able to cancel. Just to let you know, I put a space because I don't have a very good way to enter multiplication sign, and I don't like to use X here. So now I can cancel this and this, this, and this. So let's do it. Things are looking pretty good. We have it. We proved the sine rule for obtuse triangle and acute triangle. We have both cases. And of course, you can use the other, pick another pair, A and C, to prove the next part.